I'll read that again. Graphing. A display of the relationship between two variables. So variables would be your blank there and your sheet. So two variables. Now, I am going to pop down here to the graph. Here's a variable down here, okay? The quantity is listed. Here's a variable here, the quantity is listed on the y-axis, on the x-axis. Now, on the bottom is something called the independent variable. So as one variable changes, okay, so one variable is changing, that's the independent variable. Another responds to this change and changes itself. That's the dependent variable. So very important you get the difference between these two correct. So the independent one is the one that, you think about it, it's the quantity that has the agency to move itself. Okay, I am going to move. Okay, so what is it? There's a car, okay, that's driving. All right, and it is going a certain speed, let's say. And as the car changes speed, the distance away from the starting point, let's say, changes. Okay, as the car slows down, the distance also changes, but it doesn't change as fast, right? Or let's say that we have, in most cases, when we're comparing two variables, one is time. And time, because we can't really stop time, fast forward time in real life, that's the independent variable. It's the one that's the boss. It's the one that changes, and then we measure things that respond as time passes. So that's the dependent. So the variable that goes on the y-axis is the one that depends upon the change of the independent one. Okay? So if you are a dependent person on someone, that means that you respond to what someone else does, right? If they go to this movie, you want to go to the movie. If they stay home, you want to stay home. If they jump off a cliff, you want to jump off a cliff. You shouldn't do that, by the way. It's not good. Don't jump. Unless you're cliff jumping and you know it's safe and you're not, doing something illegal, I still wouldn't advise cliff jumping. So if your friend jumps off a cliff, seriously consider maybe not doing that. However, I just don't want you to die or be lame. Okay? What? What was funny about that? What was funny about not wanting you to die? What was the laughter for? Because what? I can't hear what you said. All I heard was, that's what I heard. Is that what you said?
Yeah.
Okay. You guys should do that just once in a while to mess me up. You
get mad.
You should do that. Yeah. See, I thought you already did that. I thought you were trying. Yeah, not you guys. You guys are. Okay, let's get back to the lesson here. Okay, so if your friend jumps off a cliff, don't jump off a cliff with him just because of your friend. Okay, don't be that dependent, please. All right, so time is usually dependent. Let's say I'm, okay, the basketball game last night. I was at the basketball games, both of them last night. And when you are playing basketball, okay, and you shoot a basket and the ball goes in the hoop, that would be like a change in the independent variable. Yes, there were some struggles last night. Hey, but you were close, okay? And those are going to drop. Those are going to drop. Don't worry about that. That happens. But listen. As the ball goes in the hoop, and I saw you score some, the ball goes in the hoop, the clock changes, right?
Yeah, sure.
It changes. So that's the dependent variable would be the motion of the clock. The change in the numbers of the clock depends upon if you get a basket or not. Not like that. Okay. We got independent, dependent now? We okay with that? All right. So what do you need on the graph in order to get 100% on your beautiful looking graphs? You need a title. You need a title of your graph. Okay? Please do not let your graphs go titleless. Okay? We don't want them to be titleless. So the title is often, one variable is mentioned versus the other variable or compared to or whatever, right? If you have a height, let's say is this quantity, and time, okay, so you're climbing a mountain or something, and your height over time looks like this. You stop at base camp, your height doesn't change. Then you start climbing again. Now this might look like a mountain. Whoops, that was a mistake. You didn't go back in time. You don't go backwards in time. Okay, anyways. But I don't remember my point. You can say height versus time. That's fine. Height versus time, okay, or height up a mountain versus time, or height above sea level over time, some kind of title to tell me what's on there. All right. You also need your quantity listed, height. You can say height above sea level, be as exact as you can, that's fine. And you also need the units. Okay? You guys listening? Units. So if it's meters, put like an M in brackets. See how it's brackets here? M in brackets. Down here, same thing. Time, what are you measuring time in? Seconds, minutes, hours, days, what? Years. Hours. No, not years.
Why not?
Well, you could, but climbing a mountain? You're going to climb a mountain over a span of years?
Who knows? Yeah.
Okay, 1, 2, 3, 4, 5 years. You climbing a mountain. A normal person, the whole graph would be like right here. Boom.
You take half a year to climb a mountain?
Why not? Have you ever climbed a mountain?
Yeah, it does take 5 years.
Does it take 5 years to climb a mountain? No. Okay, listen. Oh, you were climbing mountains before you came to this school. Oh, really?
Yeah, for like years.
For like years.
For 8 years.
Okay, listen, the hill in your backyard is not a mountain, okay? All right? Sorry, when you're 2, that's a mountain, but it's not a real mountain.
Exactly. She was 2
Up
before
and
she
then
came here.
down, so that would take 5 years.
Oh, to go up and then down?
Yeah.
Oh, you're going up a mountain. You're getting to the top. You're saying Yahoo for like 2 minutes.
No, go to like.
And then you come all the way down and you just like chill and you like,
It goes
and then you
much
decide,
faster down.
and then you're in the mountains of Tibet, so you run into a monastery, you decide to be a monk for the rest of your life, and then you die. No, you don't go straight down. Unless someone throws you off the mountain, when you die, that's terrible.
No, you're sledding.
So here's where you're a monk in the mountains of Tibet. You just stay up there the whole time. And you subsist off of plants and random insects and animals that make their way up that height. All right, we are descending into chaos here. I'm not sure this lesson's going exactly as I had planned. See, graphing can be fun. Let's get back to work. All right, what else? Be sure that your points are carefully placed. So on a graph that you make for me, okay, you're not going to write monk on there either. On a graph you make for me, okay, the points that you put on there, carefully placed, okay? And don't make your circles like this big. I'm in grade 2, okay? No, don't. Make sure they're carefully placed. Actually, when I was in university, I don't think I had to do this in high school. Maybe I did. But if you plot a point, what you could do is place a small circle around the point, indicating that there might be some measure of error there, and that the real point is somewhere within that little circle. So I used to have to do this, I think, in university. All of my quantitative chemistry courses and stuff like that, we had to kind of do this. A little circle around the point. I won't make you do that, but that's something you could do. But please be careful with your point, okay? If it's 1, 5 here, don't put your point here. That's 1, 5. No, it's not 1, 5. That's like a little bit more than 1, and it's a little bit less than 5. So just be careful. Got it? Okay, what's the other thing? If you have to make a line of best fit, or a curve of best fit, and a lot of times we have to do this because we want a generalization of what the data is doing. If you look at these points here, and I'll make a little bit better point for this first one. If you look at these points, they appear to be somewhat linear, right? So if you were asked to make a line of best fit, you would try and make a straight line that passes through or in between as many points as possible. And a line of best fit also doesn't start before your first point. It doesn't go past your last point. Okay? But a line of best fit, I would think, would be something pretty much like this. Now, it does not have to pass through any points, actually. And don't just connect the first point and the last point. What it has to have is roughly the same number of points above the line as below the line, roughly. That's a good line of best fit. And are you ready for this one? You ready for this? This is maybe a bit much for you, but some of you will understand this. The collective distances, okay, the absolute value of actually the square of the distances of the points above the line and below the line should be equal, or close to being equal. So that means that it's not just the number of points above the line, but that the line is sort of in between as many points exactly as possible. So the distances from the point to the line of all the points above and all the points below should roughly be the same. Okay? And the smaller that sum of those distances is, that means the more coherence you have, or the points line up better. If the points were like way out here like this, okay, great, I've got 5 below and 5 above. But this is not very good coherence. Here's a broken line graph connecting these things. And the general pattern of the graph does not follow this line of best fit, right? So lines of best fit. Now you could also, I could also ask you for curves of best fit. Okay, so let's say you have something like this. These are your data points. So a curve of best fit, and you would do as best you can to make now do I have this on here? Smooth curve or a straight line. So you would go something like this. Okay, you would go, okay, here's my smoothest curve that I can kind of pass through as many points as possible. It's really smooth. I'm going, I don't have to hit all the points, but you have to make it smooth. So I'm smooth moving. It's like an X-lax curve. Okay, smooth moving. All right, so that's a smooth curve there through as many of the points as possible. Question?
Can't you just connect the dots if it's smooth? Like,
Can't you just connect the dots? No, a line of best fit is not just connecting the dots. Okay?
For curves, you can always make it smooth. Yeah, because it's just like a circle.
Well, not necessarily. No, not necessarily. No, not necessarily. That's a good point. You can always just, you're saying you can connect the dots and make it as smooth as possible. But not necessarily. Not necessarily. What you'll find, and when we get into math, and I think we've done this actually with the graphing calculators with you guys. Some of you that were in that last math class. Now remember, if the graphing calculator did this, it would never go through all these points. Because you would have a very kind of like shallow, long, elongated curve here. Then you'd have this really sharp curve here. And it wouldn't do that. It would be a cubic or a quartic or a quintic function. And they wouldn't pass through all the points.
Like it needs to be one function.
Yeah, one function. Anyways, don't get hung up on that. But I see what you're saying. But you would never have something that goes like this, and boom, a real big kink in it, and then it's like pretty much straight, and then boom, another really big kink in it. That's not smooth enough, is what I'm saying. That wouldn't be smooth enough. Okay? But that's a little point. I don't want to belabor that point. But lines or curves of best fit kind of pass through as many points as possible, or a nice smooth curve through as many points as possible. All right. What else is on your notes there? Okay, this one. This page here, ready? Quadrants are important. Girls, listen. Quadrants are important. This is quadrant 1. If this is 0, 0, that's 0, 0, the origin. This right here is quadrant 1, and I think if you were in, pre-calculus 20 class here just before this, we would have talked about this. But this is quadrant 1. And this means that the points or the coordinates of any point in this quadrant will be a positive x and a positive y, because from center you would go to the right for the x coordinate, and then you would go up for the y, and both of those would be positive. So that's what this means. You work counterclockwise, so this is 1, and you go counterclockwise to 2.
Wait, who decided that?
Who decided that?
Yeah.
I don't have a name. I think his name might have been Bob from New Jersey, but I don't know. But why not? Why not? And here's the thing. There's lots of reasons why, okay? There is lots of reasons why. I think a lot of them has to do with trigonometry, sine and cosine graphs and stuff like that, okay? But yeah, this is 1, 2. The quadrants of your mouth, because my wife is in the dental field, they are different than this, which really bugs me. And that's why I asked her, I said, why don't you guys just go with math? She said, why don't you guys just go with, with the mouth? I'm like, I don't know.
Well,
So we're at an impasse there. But we've come over that mountain, and I can tell you right today that our relationship is in a much better place. Okay? And you too can have a successful marriage relationship even if you disagree with important things like this. It's possible. Praise the Lord. Okay. Quadrant 2. Guess where quadrant 3 is? Not over here. No. You keep going around the clock backwards, because we're backwards here sometimes in math. This is quadrant 3. Boom. Oh, by the way, did I mention the sign? Negative x direction, positive y direction. That's how you get to points in this quadrant. Negative x direction, negative y direction is how you get to points in quadrant 3. That's why it's a negative, negative. And yes, I know that looks like a little kind of smiley face almost. It's not a monkey. That looks like a monkey?
Can it have a tail?
Really?
Snowman?
Can it have a tail?
For the nose.
Okay, fine.
Snowman.
Yeah, no, well, not his drawing. Like with the actual
Wait, who said
picture.
snowman? Wow.
With the actual drawing. But
She actually drew a snowman.
she drew people and all.
She drew a snowman.
Where's the tail? There it is.
Oh, it's a monkey.
It needs ears.
Not sure.
Those are like the-
He needs ears. Where is his ears? Down here? Yeah, right there. That's good.
How high is that one?
Gotta have more fur on his face though. Lots more fur.
It has
Fur everywhere. No, it's fur. It's a monkey fur.
That's
It
fur.
needs,
Stripe
like,
tail,
two
everything.
dots for a nose.
Okay, that's all the monkey you get. That's it.
Go up and draw it and he'll say it.
We're done.
It's a good song.
No, we're not talking. No more. Hey! Monkey disappeared. My computer. Okay. So half the monkey's gone. See monkey do. No monkey see. No monkey see. He's got no eyes. That's a good joke actually. You tell a little kid. What kind of monkey can't see anything?
Mr. Maxwell's.
A monkey with no eyes. Yes. That's super funny. Okay. Don't you guys get that?
No.
A monkey with no eyes can't see. There's no eye in monkey. That's a good one too. Remember, we got to pull together. We can win this game. There's no eye in monkey, guys. Okay? Look out for each other. Quadrant 4 is over here. Plus minus, guys. Watch this. Positive x direction, minus y direction. Okay.
There he is.
There, he's back. All right. So quadrant 3 is monkey quadrant. Okay, that's fine. We can remember it that way. Monkey quadrant. Okay. All right, this is so easy. This is like elementary baby stuff, so you guys are going to be, I don't know if you're going to be happy or sad. I don't know if this is beneath you or not. So here's a table of values underneath. Tough for you to see. It's kind of small. I'm sorry. Kind of. X, Y. So this is an x coordinate that goes along with this y. So the first point is -3, -10. And of course, we count from the center always, and we always do the x first. Negative means left. So we go 1, 2, 3, and then we go -10, which is 10 down. So the y direction, positive is up, negative is down. So I go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right there. And that's my point, 310. -3, sorry, -3, -10 in the monkey quadrant. Now, if you want to label your axes, go ahead. See if I care. 1, 2, 3, 4, 5. That's -5, 6, 7, 8, 9, 10. That's -10. You can label them all if you want, but it's going to get pretty busy if you do that, so I wouldn't. And you can do that for all 4. Now, the next one is -10, -6. Okay, right away I know that what quadrant this is in. It's in the monkey quadrant, right? It's in the third quadrant. So I'm going to go -10. I'm going to count by 2s now. 2, 4, 6, 8, 10. Okay, there's 10. And I'm going down 6. Oops. 1, 2, 3, 4, 5, 6. Yeah. So there's -10, -6. Okay, so your tough job here is to just plot these points. I know. Crazy. So what I'm going to do is I'm going to show you what my completed graph looks like after I give you a few minutes to finish this. So here are the points. Right there, I'll zoom in for you if you need to see those up here. Go ahead and plot those points. We'll see what the graph looks like in a minute. Okay, here's what they should look like. Maybe a little bit tough to see. I'll zoom in a bit here. Frozen, unfrozen. Okay, so I put little X's on there too just to be easier to see, but this is where the points are. Yeah, you should label them. So we have 3 in this quadrant, 1 over here, 3 in this quadrant over here. Okay, so overall, your points should look something like that to match up. All right, so this is the next page. You are going to need some graph paper, as I mentioned before. So some of you have that graph paper in your locker. You went and got that. Okay, anybody not have graph paper at all right now? Okay, if you can borrow a page from a friend, that would be great. I could probably dig up a paper too over there if you want. So I'm going to just get started on this activity. If you need some graph paper, I can get you that in a few minutes. Okay, so there are 2 questions here. Everybody watching? There are 2 questions here. Your job is to graph the following data on a carefully labeled grid. Now, the grid is like your graph paper with a coordinate plane there with the grid, okay? The XY axis, just like we had on the previous page there. So I also want you to, after you've carefully, and I should talk about one thing about creating your actual graph, okay? Let me talk about that. But you're going to draw a line of best fit or a curve of best fit for each. So as we mentioned, you're going to draw a straight line with a straight edge if the dots appear to be, or the data points appear to be somewhat linear. If they appear to be curved, then you're going to draw a smooth curve through those, okay? Now, let me just go back real quick to, okay. I guess one thing I didn't really get to or talk about was the scaling, and I think that is on your paper there. So the scaling is important. So when you're creating, the scale, which didn't want that to be all erased, but when you're creating or putting the points on a blank graph, okay, if there are no negatives in the x and no negatives in the y, you really don't have to put these axes on. You can just kind of start it like this blue graph is right here, okay? So I don't know, you have to decide if there are any negative values that you have to include in these 2 questions, and it doesn't look like there are. So you could just have a y-axis here and an x-axis here. Okay. So you're going to have to title it, you're going to have to put your quantity and your units and all that sort of stuff. But the scaling part, here's what you can't do, okay? Here's what you can't do. You can't just take where was I? You can't just take these numbers right here, 1.5, 2.5, 3.5, 8, 11, 15. You cannot just take those numbers and list them here. 1.5, 2.5, 3.5. You can't just do, like 3, 8, and then 25, and then like 40. You can't just do that. Why? Because every graph will turn out to be a straight line. And that's not the way the graphs are supposed to be. So the scaling is very important. Is this an important question?
Yeah.
What's up?
Could you have a different, like for the x-axis, could you
Yep.
go up by a certain amount of numbers, like
Yep.
2 and then
It's
y
different for the y. Yes. So the scaling on each axis does not have to be identical.
Okay.
But the scaling has to be appropriate so that you use as much of the graph as possible, and it has to be evenly spaced. Each little tick mark has to be the same unit. So each space has to represent the exact same amount. Another question?
Since this sequence is like the same amount, does it matter if you would
It
start
does
with-
matter.
Okay.
Yes, it does matter, because you can't start with, let's say, you can't start with, in this example, you can't start with 1.5 here and then go to 2.5, because already you're messed up. Why? Because this space is 1.5, this space is 1, and that can't happen. So even if this is all 1, this is all 1, this is all 1, even if this happens, as soon as you've got this, it's not right.
What if you left an extra 0.5 space?
Okay, so again, what you want to do on your graph, you don't want to just start with numbers up here like this and then continue on. You have to have everything kind of filled in evenly. So you don't have to have the exact numbers that are on your list on the graph, but you do have to have everything appropriate. Okay, so what does appropriate mean? Appropriate means if you have a range of, in this example, 1.5 to 7.5. So you could do ones, but look at this. 1, 2, 3, 4, 5, 6, 7. This is not appropriately spaced if this is the edge of your graph over here. Okay? Because you don't want your graph to kind of be in just a portion of the space provided. You want to stretch it out as much as possible. So what that means is that you might have to do this. You might have to go 2 points, 2 spaces for every 1, then 2. See, you might have to spread it out a little bit like this. Then you'll have a better 5, 6. So that's much better. See, we've spread that out. So that's the scaling I'm talking about. Each space has to represent the exact same amount on a particular axis. And you want to spread your data out so that you can spread your points out. So your graph can be a little more precise. So up here on the y-axis, this does not have to be the exact same scaling. It can be different. So in another example, so in this example, it's a random example. Let's say This is time in years, okay? And this is like height of a mountain, okay? We're going to take 7 years to climb a mountain. And let's say this is like, 1,000 feet. And this is, 3,000 feet, right? And 5,000 feet. So each space is 1,000 feet, whereas each space was a half of a year. So those can be different, but they have to be consistent. Within each axis have to be consistent. Does that make sense? Okay, now is there a question? Okay, for question number 1, which is the dependent variable that goes on the y-axis? Which is the independent that goes on the x-axis? Which do you think, look at the numbers, which do you think has been manipulated? That's the independent variable that has been being changed. And which one is responding to that change? Okay, you think the independent is the mass. Can you tell me why?
Because it goes up in a consistent amount.
Yeah. It looks like someone is actually, a mind behind this is actually adjusting the mass and then measuring the height. Now, we don't know what the context is here, but that I would say that you're exactly right. Someone is just adding 1 kilogram to every trial. And so whether it's how high you can throw this with the one hand or something. You've got 1.5 kilograms, and with one finger you can flip it up 8 centimeters in the air. I don't know. But it does appear that the mass is the independent, the height. So
mass is
height versus mass, I don't know, mass versus height. I would probably suggest that you do the independent variable versus the dependent variable. So the y versus the x. So height versus mass.
So height is y or x?
The mass is the independent variable, which is the x-axis.
Yeah.
The height is the dependent, which is the y. Yep. Okay, and then I'll just quickly talk about number 2, and then I'll let you guys work for a bit. So speed, here it's indicated this is the independent variable, and force is the dependent variable. So we adjust the speed of an object, and then we calculate how much force that object has with this amount of speed, okay? So again, smaller speed has a greater force. So I'm not sure what this is actually, I'm not sure what this is actually measuring, but we've got speed and we've got force. So independent, that's going to be the x-axis here. This is going to be the y-axis. So the situation for this might be something like, here's the speed, and this is the force perhaps in the opposite direction or something. Like how much force it takes to... Nope, that still would be the other way around. Maybe this is force applied to a moving object. This is the resulting speed, because when you have less force applied to it, it's going faster. So this would be a force in an opposite direction, maybe. I don't know. It doesn't matter. The context doesn't really matter, but your graph here can be made. Okay. The slope of the tangent line, I think there's one more thing I need to talk about. For a straight line of best fit, find the slope. So how you do that is you remember slope is rise over run, and you have to, everyone listening, you have to use a point that's on the line of best fit. You can't necessarily use your data points. If they're not on the line of best fit, you can't use them. So you have to use a known point that's on the line of best fit to calculate your slope. Okay, go ahead. You have the rest of the class here to work on this.